Hi. Well, today we finish with the playlist about basic points of the buck converter, and in this video we are going to study the voltage and the current of the switches. And this information will be very useful in order to choose in the future the MOSFET and the diode that we need in order to implement a prototype. So let's start with the video. As in the case of the previous videos, we have some considerations, but essentially they are the same as in the case of the previous one. So I'm not going to repeat them. Uh, the only thing that I want to point out here is the notation that we are going to use in order to evaluate voltage across a switch and current through a switch. In the case of switch A, we evaluate the voltage across the switch in this way, with the plus sign here and the minus sign here. This is VSA. And we evaluate the current like this. Regarding switch V, we evaluate the voltage in this way and we evaluate the current in this way. It's a little bit different. Well, so now let's see if we are able to determine the current and the voltage and the current waveforms for both switches. So here we have the schematic of a buck converter, but we don't have the switches. What we are going to do is to replace them by a short circuit or by an open circuit, depending on the circuit state. So in order to do that, we need to remember that we have a control signal like this one. This is the control signal for switch A. In the case of switch B, if we use a diode, we don't need the control signal. If we use a MOSFET, is the complementary one, is the complementary to the control signal that we see on the screen. And well, as you can see, the period is the switching period, is a pulse width modulated voltage, so we have a duty cycle D. And well, what we are going to do is to draw here the voltage across switch A, and we are going to draw here the voltage across switch B. Well, first of all, in a state number 1, which is the one from t equal to 0 to t equal to d times t switch, what we have is that switch A is on. So we can put here a short circuit. And in the case of switch B, as we saw, I think that in the first or the second video, switch B is an open circuit in this case. Okay, so if switch A is a short circuit, ideally the voltage across it is 0. So let me put here 0. Okay. Well, if you apply here in this mesh Kirchhoff voltage law, you will see that the voltage across switch B in state number 1 is the input voltage. So basically, during state 1, switch B blocks the input voltage. Okay, this level is VI, the input voltage. Well, what happens in state number 2 from t equal to d times t switch to the end of the period? Well, in that case, switch A is off, so we have an open circuit here, and switch B is on, so we can put here a short circuit. Well, if we have a short circuit in switch B, that voltage is 0. And if you apply again Kirchhoff voltage law across this mesh, you will see that switch A is blocking the input voltage. So essentially, during state 1, switch B blocks the input voltage. During stage 2, switch A blocks the input voltage. And then this is periodic, so we can complete here the waveform. We do the same for switch V, and as you can see, the waveforms are just complementary. Well, so the conclusion in this first analysis is that if we have to choose the switches, we must ensure that they are able to block the input voltage. Okay, so this is something that we will use in the future. Well, let's talk about the current waveform in both switches. Again, we are going to consider the control signal for switch A, and we are going to replace the switches with a short circuit or an open circuit. In this case, we are going to draw here current through switch A, and we are going to draw here current through switch B. And in this case, it will be very useful to put here the inductor current. We already know the shape of the waveform because we studied that in, I think that in 2 videos before this one. So it as I said is very useful because, as we will see, in one state one switch is driving all the inductor current, and in the second state the second switch is driving all the current. Okay, let's see that. In state number 1, this one, what happens? Switch A is a short circuit. Switch B is an open circuit. So basically the inductor current flows through switch A, and the current through switch B is 0 in this state. So let me draw this. We have something like this, but let me put this, and in this case we have 0. Now what happens in state number 2? State number 2 is this one. We have to think about the equivalent circuit of the switch. In the case of switch A, the switch A is off in this state, so we put an open circuit. Switch B is on, so we put here a short circuit. Conclusion: all the inductor current is flowing through switch B in this state. So essentially here we have all the inductor current flowing through switch B, and in the case of switch A, the current is 0. And then we repeat the sequence because everything is periodic. Okay. So conclusion: in state number 1, all the inductor current flows through switch A. In state number 2, all the inductor current flows through switch B. In this case, we are going to consider different aspects about a waveform. As in the case of the voltage waveform, the first one is the maximum value. So if we want to evaluate the maximum current through switch A, is very easy to see that is this point, and basically is the maximum current we have in the inductor. So we can put the maximum current through switch A is the maximum inductor current, and as we saw in a previous video, This is basically the average current through the inductor, which is the output current, plus half the peak-to-peak current ripple, as you can see here. Well, if you repeat the process for switch V, the conclusion is the same. Maximum current is this one in that case, and is essentially is the same as the one you have on the inductor current. So the result is the same. So as I said, in the case of the current waveforms, we need to evaluate not only the peak value, but also other aspects of the waveform. In particular, we need the average value and the Rho mean square value. Basically, they will be very useful, for instance, if we need to evaluate in the future the conduction losses in a MOSFET or in a diode. So let's see the expressions. I will go very fast here. Remember that in order to do the average value, in this case of the current through switch A, what we do is 1 over the switching period, integral from 0 to the end of the period of the current waveform. Okay, and if you evaluate that expression, taking into account the waveforms you have on the left side, you will see that basically it's the duty cycle times the output current. Why duty cycle? Because it's the amount of time the switch is driving current. Why the output current? Because it's the average inductor current. As I said, it's very easy to obtain this expression by solving the integral expression. Well, if you do the same with switch V, the solution is very similar, but the difference is here, instead of D, we have 1 minus D because switch V is driving current for 1 minus D times the switching period. That's why you get that expression there. Okay, and very quickly, let me show you the Rho mean square value expressions. I'm not going to put the general definition. You can obtain this expression in Google. And let me point out that in the case of switch A, that Rho mean square value depends on the output current, duty cycle, and peak-to-peak current ripple. And similarly, in the case of switch V, it depends also on the output current, duty cycle, but in a different way, instead of D, 1 minus D, and also on the peak-to-peak current ripple. So as I said, these expressions will be very useful, for instance, for evaluating conduction losses in the switches. Okay, so with this, we finish with the playlist about basic points of the buck converter, and these videos will be very useful in order to see in the future more complex things that will be very interesting. So thank you for watching this video and all previous videos, and see you soon.